For many developers, designing a suitable filter is tricky, as you're confronted with a myriad of design choices and parameters. Sure, it can be done in Python, but it's slow and cumbersome. For the hand gesture demo that we're looking at, the processing can actually be broken up into blocks. As seen in the diagram, the MEMS sensor data are first fused and then cleaned by the DSP algorithms before being passed into the ML model for classification. This forms the essence of true real-time edge intelligence, where we combine the strengths of both DSP and AI to improve classification accuracy. Looking at the data cleaning aspect, we can actually make the filtering task somewhat simpler by working with linear acceleration data from our MEMS sensor, whereby gravity and some low-frequency drift are removed by the sensor fusion block. This circumvents the need for a high-pass filter, whose low-frequency cutoff would otherwise introduce massive latency, making the system far less responsive for real-time feedback. However, what remains is high-frequency noise that will reduce the accuracy of our ML model. This is where the ASN Filter Designer can help, as it allows you to design and validate a range of filters both quickly and interactively while visualizing the results in real time. In this way, the ML model receives the clean features it needs for high accuracy. Opening the ASN Filter Designer, we can set up a suitable filter for our hand gesture demo. Our goal here is to reduce the high frequency noise while preserving the overall shape of the gesture waveform, which is critical for our feature extraction phase. To achieve this, we select a linear phase Kaiser FIR low pass filter with a cutoff at around 10 Hz. The idea is that the filter removes the unwanted high frequency noise, and the linear phase preserves the shape of the waveform so the features extracted for the ML model remain accurate. As seen using the interactive interface, the filter specifications can be adjusted directly with the mouse, and the frequency response charts update in real time, providing you with an instant visual feedback. Once the filter has been designed, the next step is to validate it using real data. With the ASN Filter Designer's Signal Analyzer, validation is straightforward. A captured CSV file of accelerometer data from the SDS framework can be dragged and dropped onto the canvas, bringing up the data import wizard. The data import wizard will automatically check the imported data for errors, such as nans and ints, etc., and then all of the data into columns. Any header line data can be skipped by setting the skip header lines value respectively. We know that our data is triaxial accelerometer data, that is X, Y and Z axes data, with an extra column for the time base. Therefore, if we wish to import the X-axis data, we can simply click on the header for the second column, B. The tool will automatically ask you to recheck the data, and upon clicking on Save will save the selected data as a single column comma separated file needed for the ASN Filter Designer. This new CSV file will then automatically be loaded into the tool's signal generator for playback. Clicking on the play button, we can then begin streaming the data through the filter. The tool's time offset function also allows us to align the input and output signals for clearer analysis. Here it can be seen that the high frequency noise has been suppressed while the main gesture features remain intact. Note that we can fine-tune the filter specification graphically with the updated results displayed instantly in real time. With validation complete, the filter is ready for deployment. Using the ARM code wizard, the design filter can be exported directly via the CMSys DSP library for efficient real-time execution on any ARM Cortex-M processor. Alternatively, the Python deployment wizard may be used for integration within your SDS project. So let's summarize what we've seen. The ASN Filter Designer removes noise and allows you to obtain clean, reliable feature data, directly improving ML model accuracy and responsiveness at the edge. And with its seamless code generation export capability to Python and C, it fits naturally into the ARM SDS ecosystem, bridging the gap between raw sensor data and the ML model.